include this behavior, notice that so some people memorize and they say, oh, it opposes the change in the flux. So the magnetic field always has to be opposite to what the external magnetic field is. In this case, because the magnetic flux was getting bigger, the external one due to the magnet, right? The magnetic field induced by the current is in the opposite direction. But what about in this case? In this case, the magnetic flux was getting smaller, so it's like the ring is helping it. So it has to produce a magnetic field in the same direction that the external magnetic field is in. So I think I wrote a couple of sentences to this effect in my notes. I mean, Lenz's law simply says that the induced current in the loop, right, will be such as to oppose the change in the flux. End of the sentence. Now, what does that statement mean as far as if the magnetic field is increasing or decreasing? Right? So then I added this couple of comments here. So Lenz's law, here it is. What did I say? If the magnetic flux is decreasing, that was the case over here when I pulled the magnet farther and further away, right? Then the induced current in the loop will be in a direction so that the magnetic field that it generates, the induced current generates, adds. In other words, it's in the same direction as the external magnetic field. But if the magnetic flux through the loop is increasing, like this other picture over here when I move the magnet closer and closer to it, then in that case the induced current in the ring will be in a direction so that the magnetic field that it generates, that's the induced current, subtracts, meaning in the opposite direction to the external magnetic field. But Lenz's law said in one sentence, it's just the current will be in a direction such as to oppose the change in the flux. Full stop, period. Now, what does that mean? In some cases, it will be in the same direction as the external magnetic field, and in other cases, it will be in the opposite direction. It always opposes the change in the flux. So, I can generate an electric current in this ring without connecting it to a power supply, to a function generator, to a battery. I can get a current going in this ring, one way or the other. All I need is a magnet. And all I need to do is to change the amount of magnetic field that goes through the magnet. Through the ring, sorry. And I can do that either I hold the ring steady and I move the magnet in and out, or I hold the magnet steady and I move the ring in and out. Or I can hold the magnet and the ring, but then just rotate the ring. And yes, the more quickly the change in the magnetic flux takes place, the higher will be the magnitude of the induced voltage, and therefore the higher is going to be the current induced in the loop. So let's consider a particular example where I apply this, and that. Let's do a simple example, and then I'll do an extra example which is a little bit more involved. So let's consider the following. There are some cool questions in chapter 29 in the textbook for which I wrote down solutions, where there's a situation going on, and then it asks, will the induced current be this way or that way or blah blah blah. But they're very interesting questions. You have to think through it, and but once you understand Lenz's law, it'll be simple. So I highly encourage you to go over those questions in the book on Lenz's law, because they're very, very good questions. It's kind of hard to draw it in 3D. Okay, so let's consider this case. Let's call it an example. What if I have a conducting rail? So it's a metal rail, and I have more metal here, and there's a lamp over here, like a light bulb, with resistance R. I don't know, maybe this is a lamp that can turn on and off. And then more conducting rail, so this is a conducting rail. And there is a crossbar, a bar over here that can slide on this rail. And the length of this thing is L. So I have like a loop over here, right? But it's open on this side. And what if I take a magnet, and a magnet, and I put it like this, and I put it like this, with the north end facing that way, the south end facing that way. So there's going to be a magnetic field going through this loop. How about I make it simple for the sake of argument, for the sake of the discussion, and let's say that the magnetic field exerted by the, or generated by the external agent is uniform and into the board. It's all over the place. If you like. So this is some external, uniform, same magnitude, same direction, magnetic field. I call it external. And the X means into the board. All right. What is notice, there are no batteries. There's a this resistor represents like the resistance of the whole thing. Or well, that's a lamp over there. The length of that bar is L. It can slide without friction. Or maybe with friction. But the bar is is connected to these rails. It's two parallel conducting rails. And we have a lamp connected between those two rails. Right now, if I hold the bar over here, is there a current in this loop? No, how do you know there's no current in the loop?
Because there's no change in magnetic flux.
Because what?
There's no change in magnetic flux.
There's no change in the amount of magnetic flux through this thing, right? Okay? Good. So what I want to do is this. What if I grab this bar, I physically grab it with my hand, and I go, and I pull it to the right. When I put it to the right, will there be a current in this loop?
Mm-hmm.
And the lamp will light up.
That's even if the area changes as well? It's not a ratio?
Well, remember, magnetic flux is, this is a uniform magnetic field, so I can just write it like this, right? And this will be the magnitude of that, which is the same everywhere, times the area, times the cosine of the angle. This angle has to do with the direction of the area vector and the magnetic field. The area vector here doesn't change any direction.
Okay.
And the magnetic field doesn't change any direction. So what's changing over here as I pull the bar to the right? So as I change the area, I change the flux. There's going to be an induced voltage, which will lead to an induced current. So I want to generate electricity. I got to change either one of these three or a combination of that. But as long as they change, there's going to be a current. In this particular case, I'm grabbing it and I'm going boom to the right. And suppose I pull it, I say that I pull it at constant speed. So the speed is constant. So we'll do an example where the speed is not constant, but let's say that the speed is constant. Okay? So we pull the bar to the right at constant speed. Okay? That's us. First question. What is the magnetic flux through the loop? Should I specify the B in there? I mean, we're talking about magnetic flux, so should I just call it phi? Or do you like to see the B as a subscript?
Kind of used to the B.
You like the B? Okay. Through the loop. So what is that? So what is the magnetic flux? It will be, well, the magnetic field is into the page, right? So I'm just gonna do it like this, right? So this will be the magnitude of the magnetic field, right? If I don't write the arrow above the letter, it means the magnitude of the vector, right? Times the magnitude of the area vector, times the cosine. What is the angle between the magnetic field vector and the area vector? Well, the magnetic field is into the board. The area vector has to be perpendicular to this loop. It could either be out or into. How about I choose into? If I don't pull it, first of all, there's no current. If there were a current, I could say, oh, the magnetic dipole moment, so the area, I'm going to choose it this way, I'm going to choose that way. But in this case, it's arbitrary because there's no current in it until I pull it. But let's say before I pull it, what's the magnetic flux through it? So what's the angle between the magnetic field and the area vector? What? Which way is the magnetic field pointing?
0 degrees.
Into the board. And which way is the area vector has to be perpendicular to the plane. So it's either into or out. So let's choose it into. So therefore it will be 0 degrees. So it will be B times A. Now, what is the area of this loop right now? Well, how about we give it some dimensions? What if I call this distance over here? What if I call it x? That's not the same thing as that. And the length of this is L. So what is the area of that loop? What is it? What's the area of the loop?
X times
L times x, right? That's the magnetic flux through it. Next question. This is when I pull it, right? What is the EMF induced in the loop? Let me just calculate the absolute value of it. The minus sign is to tell me the direction of the induced current, but to figure that out, I'm going to use Lenz's law. So, the EMF, which is the induced voltage, right? If you want to call it like that, that's also fine. Is what? Is the derivative of the magnetic flux with respect to time. There's a minus sign in there, but I'll do this if you like. Now, what is this would be ddt of, what is the magnetic flux? BLX, correct? Now, which of those parameters is changing with time? On which quantity should the derivative with respect to time be taken?
X is changing with time.
X is changing. The length of the bar is not changing. That's a constant. And the magnetic field, the magnitude of it is constant. So this derivative acts on X, and I get B L dx dt. Or the inducement. And what is the x dt? What is the rate at which this distance is changing? What's that? V, correct. The speed with which I'm pulling it. Right? The rate at which that bar is moving horizontally is the speed. So the EMF, if you like, or the induced voltage, is VLV. And this answers that question that you were asking. So the faster I pull it, the greater is going to be the induced voltage. C, what is the induced current? I induced. Well, I induced, the induced current will be the induced voltage by Ohm's law, which is the EMF, right, divided by R. So that would simply be BLV divided by R. Now, how about we include the direction of it? Will the induced current in this loop, which includes the lamp, will it be counterclockwise or will it be clockwise? What do you think? And why? Counterclockwise? Why? How do you know it's going to be counterclockwise?
It's going to want to oppose. So
Okay, go ahead. So how does it oppose it? So
it comes out of the board, and that means
why does what comes out of the board?
the opposing magnetic field that the current is going to generate.
Why not into the board?
That would be adding to the current that's already being added to. I mean, the EMF that's already being
It would not be happy.
Right, so so the way I have it is like 1, 2, 3, 4, 5, 6, 8, right? I got 1, 2, 3, 4, 5, 6, 7, 8. When this bar gets to here, it'll add 3 more, right? So then it'll be 11. So the more I move the bar to the right, then it's gonna get more magnetic field lines, right? So therefore, oh, it's increasing. No, it's gonna be this one. So it has to produce its own magnetic field going out, pointing out of the board. But if in this loop it has to produce a magnetic field, this is the induced magnetic field, which means the magnetic field produced by the induced current. That's what that means, right? And it has to be out of the board. Therefore, it has to be in the bar. Does it have to be up the bar or down the bar? It would have to be up the bar. In the resistor, it will be up or down the resistor? Down the resistor. Please be careful. I put problems similar to this in the final exam, and I ask, what is the direction of the induced current in the resistor? And you'll be surprised. Some people say to the right, others say to the left. So I don't know what question they read, but you can lose 3-4 points automatically for not reading a question carefully. I mean, if the current is through this resistor, the way that the resistor is positioned is either up or down the resistor, not to the right or to the left, or out of the board or into the board. Those answers are very bad. Right? It probably means you're just guessing, but guessing it's not even an educated guess, right? If you don't know, and you're going to make an educated guess, say, down or up the resistor, not to the right or to the left, because, the resistor is not horizontal, so it could have been to the right or to the left. So if you want to finish this answer over here, so that you also include some, you can say counterclockwise, right? The induced current is going to be this many amps in the counterclockwise sense in the circuit, which in the resistor, it will be down the resistor. In the bar, is going to be up the bar. Now, let me address this other question to show you how I want to say cute, but I think is it okay? Yeah, why not? I want to show you how cute this is. Remember the opposing field? I erased the minus sign. Think of it this way, right? Here's this loop. Well, this loop over here, it's got rails, right? And there's a magnetic field going through it, and the loop says, I'm getting vague in this magnetic field. And it's the same, so I'm not happy. Right? And then I grab that thing and I pull it. They said, no, don't pull that thing. Because if you pull it, you're changing my flux, and I'm unhappy. Then I gotta do something. I don't want you to pull that thing. The loop, the electrons don't speak English, they don't speak Spanish, they don't speak, some Portuguese, a little bit of Italian, they don't speak any of that. So they can't tell me, stop pulling the thing. But the loop has taken physics to 80. And it says, I remember this equation in chapter 27. Right? There's an external magnetic field into the board, right? The length of that bar is a number, right? I don't want him to pull me to the right. I want him to feel a force to the left to oppose the fact that he's pulling. Right? So the bar wants to exert a force. The loop wants this bar to experience a force to the left. It's like it says, if we create a current in this bar, in which direction should it be? So that he, as he pulls to the right, he encounters don't pull it to the right. So the force, me, I grab it like this, and that's the force exerted by me. And then the loop says, no, I don't want you to do that. I'm going to exert a force in the opposite direction. Let's say by the loop. Or maybe the induced force. So you tell me, right? This is just a number here, L, right? Cross, this vector is into the board. So what would have to be the direction of this current induced so that that current crossed into the board gives me to the left?
Across in.
Can you see that it has to be, the current has to be in the bar, it has to be up. Because up, if this is up cross into, will lead to a force to the left. To make it harder for me to pull it. Because the loop can talk to me and tell me, hey, stop. So it says, how do I get it to stop? How about we make a current in the circuit, precisely in the bar that he's also pulling, so that bar, right, has a current in it, and that bar has a current in the magnetic field produced by God knows what, and that current in this bar interacting with that external magnetic field that's already there will result in a force to the left to make it difficult for me to pull it, to oppose the change that I'm causing to this field. Isn't that cute? Well, how about I give you another cute argument? Here's another one. The loop also remembers from chapter 27 this equation. Right? So here's the loop. Let's forget about that for the moment. Right? And the bar is right here. The bar is metal, right? So what does it have? It has free electrons, right? Well, let's think of a free electron in there. Maybe I'll use a different color for that. Let's think of a free electron. There's a whole bunch of free electrons in the bar, right? There's a free electron here. When I grab that bar and I pull it to the right, the electrons don't stay behind. They go with the bar. So all of a sudden I have these free electrons going to the right. So the electrons are going to the right, cross into the magnetic field, which is into the board, all in the direction of that cross product. What is the direction of to the right, cross into the magnetic field? Up. To the right, cross into the magnetic field is up. So this cross product will be up. But don't forget, electrons are negatively charged. So the force on them will be down. But remember, if the free electrons move down, which way do we say the current is directed? Up. There are three different ways to figure out the direction of that current in this loop. You can access this, or think about that, or Lenz's law right away. With Lenz's law, it's like, right away you said, oh, it's gotta be, current has to be counterclockwise, right? With Lenz's law. Either way, there's gonna be a current down the resistor, this many amps, and in the loop, it'll be counterclockwise. In the bar, it's gonna be up the bar, in the resistor, it's gonna be down the resistor. So let me now discuss this exercise.